So we, in this previous lecture, we described the theorem that x1, x2, xn are IID random variable with common variance sigma square, and a1, a2, n are real with the summation is 1. In a1 x1 plus x2 a1 xn, which is a linear combination of x1 x2 xn. If the summation of this somewhere all this coefficient is 1, then it is called the convex combination. This, so any convex combination, the variance is minimum if this is if you take the mean x1 x2 xn by n. So this we have to prove. The proof is just trivial, like that proof is very important. That since this variance, we know what is the variance. The variance of S is nothing but that sigma square sum over I equal to 1 to n ai square. But we know x1 plus x2 plus xn are 1. But so the problem is you have to find the minimum value. What is the minimum value of that sum over ai square? So, but given that your sum is 1, that sum is 1. So once the sum is 1, then what is the minimum value of the a1 square plus a2 square plus an square? That is a problem. That, but this is trivial in this sense that we know this inequality that somewhere some xi square I equal to 1 to n. This is actually greater than or equal to that 1 by n is greater than or equal to 1 by n sum over I equal to 1 to n ai whole square. This inequality we know. This is sort of variance is greater than or equal to 0. Some variance. So the average of the squared is greater than the square of the average. That we know. But this is just 1. You know this is 1. It is given that summation is 1. So it is just 1 by n square. So then what? Then ai square, the sum over ai square is nothing but greater than or equal to 1 by n. So whatever you take ai is this summation square of the summation, summation of the square is 1 greater than or equal to 1. So when it will be minimum, the minimum value is just 1 by n. And when it will be minimum, the equality hold, we know this equality hold. When this equality hold? Sorry. We know this equality holds. The equality hold. That equality hold. If and only if all these ai's are equal. All these a1, a2, all these are equal and equal to. Obviously, this if they're equal, then that must be equal to 1 by n because their sum is 1. So this result is that for every convex combination, the mean, the variance of the mean is the least. And we use this in statistics, in inference theory for MVV, minimum variance unbiased estimator, something like that. So we know the minimum variance unbiased estimator is x bar. So this because of this variance is minimum. And we know to unbiasedness. So since the summation of this AIs are 1, that's why it's unbiased for IID case. Next, we define the most important part of this talk is the moment generating function. This is most important part. So what is moment generating function? Now, we already defined the moments. Now, the most important definition is this: the moment MGF, the moment generating function. So again, let x and y are two random variables. Now, if this expectation exists, that it may not be exist, e to the power t1x plus t2y exist. So remember, no need of taking the mod value because the e to the power anything is always positive. We know the e to the power x is positive for every x. So no need of taking the that mod value. If it is exist, that is the finite for that all this t1 less than some h1, and mod of T2 less than some H2. So T1 lies between minus H1 to H1 and T2 lies between minus H2 to H2, maybe equal, maybe the bound because maybe equal for some where this H1 H2 are positive real. Obviously that's not positive, cannot be H1 cannot be negative. If this exists for this for some then we write this expectation as moment generating function, that M T1 T2 joint moment generating function. This expectation we write as this. Remember, if you take T2 equal to 0, then this is expectation of e to the power T1. So it's the moment generating function of the single random variable x. So this is called moment generating function we write and call it MGF, the moment generating function of the joint distribution xy, or simply MGF of xy. So MGF of xy. This is very, very important. There are several generating function. Is a moment generating function, then there are characteristics function, probability generating function, cumulants, but the moment generating function and the characteristic function are most important generating function, because other function may or may not exist. Moment generating function may not exist, but characteristic function always exists. But when this moment generating function exists, then this is much easier to compute something or prove something using moment generating function rather than characteristic function, because characteristic function involves some complex analysis, complex variable. That moment generating function is a real one. For the characteristic function is complex analysis, analytic function. These are important, isn't it? That's why the moment generating function is so useful and important, unless if it does not exist. If it does not exist, then we go with the characteristic function. But some proof are very easy. It is not easy with the moment generating function, but some proof are very easy with the characteristic function. If you're using the complex analysis part, it's not the complex number, it's the complex analysis, like real analysis, like a real function. What is a real analysis? Limit, differentiability. Similarly, in the complex number, it's just a complex number, complex algebra. But we need some complex analysis, which is called the analytic function or polymorphic function. Some other theorems of in complex analysis we need. We will not going into this. We just now we go through the MGF a little bit. We go through the characteristic function. So this is called this, and the theorem is this moment generating function unique? Yes, this moment generating uniquely define this. So if xy, the distribution of xy is given to us, then we can easily find the moment generating function. But if moment generating function is given to us, we can easily find the distribution function also. That means there is a one-to-one correspondence. If the distribution function is given, the moment generating function is there. If the moment generating function is given, the distribution function is there. For every distribution function, there is a unique moment generating function. Only one moment generating function. There's a theorem. But the proof is tough. This proof is really tough. This is called inversion theorem. So we omit this proof. This proof needs some hardcore real analysis part. So the MGF T1, T1, T2 is uniquely determines the joint or the marginal, obviously in the joint then marginal, the joint distribution of x and y. And conversely, if MGF exists, then it is unique. Uniquely determine the joint distribution of this. And if MGF exists, then it is unique. If MGF exists for, by the way, for some distribution, MGF may not be exist. So given a distribution, the MGF may not be exist. But if it is exist, then it is unique. Similarly, if something is given, that means what happened? That means for a distribution, moment generating function may not exist. But if the moment generating function exists, then the moment generating function is unique. You can't have two moment generating functions. Similarly, for two different distributions, the same moment generating function may not exist. Same moment generating function cannot. If the two distinct different distribution, the moment generating function must be different. So, for two different distribution, say there are two distribution, and both the distribution have the moment generating function exist, then this moment generating function must differ. That's why the for a moment generating function, given moment generating function, the distribution is uniquely determined, and conversely, if the MGF exists, it is unique. Remember, the moment generating function may not exist, but if it is unique, exists, then it is unique, uniquely determined by the distribution function, and the given MGF distribution function is also uniquely determined. So proof from it, because it is a tough. So next corollary is this: the moment generating function MGF T1, T2, two variable, is completely determined by the marginal. That is the important. It's completely determined the marginal. So once the join is given to us, the marginal is automatically determined. Completely determine the marginal distribution of X and Y. And what? That moment generating function at T1 at 0, T1 T2 is 0, then it is just moment generating function of X at T1, and moment generating function 0, T2 is the moment generating function of Y at T2. So this is important. This color is very important. Now the question is why we call this as a moment generating function. Is this function generates a moment? Yes, this function generates a moment. This is a generating function basically. This function generates the moment, different moments. So how this moment generating function generates the moment? So next theorem is this. Next theorem tells us how this moment generating function generates the moment. So now, if that moment generating function exists, say this T2 exists. Remember that T1, T2 is lies between minus H1 to H2. So it is not just lies between say 3 to 5, not just like lies between 5 to exists between say 7 to 9. It's not that, or minus 7 to minus 3. It is just from minus 2 to 2 or minus 5 to 5. Like so, zero contain always. Zero always there. Zero contained in this domain. So if this exists, then if the moment generating function exists, then all the moments exist. Then the moments of all orders of XY exist. And how do I know this? What is the moment? The moment, the expected value of x to the power say m, y to the power n, mn are two positive or maybe non-negative zero, non-negative integer. This moment of the order m plus n is just what? Can we find from the moment generating function? Yes, we can find from the moment generating function. It is just a partial derivative of the m plus nth order, partial derivative of this moment generating function T1, T2, M T1, T2, and this partial differential with respect to T1 M times and T2 the second coordinate N times. And then you have to evaluate this value at that point T1 equal to T2 equal to 0. So remember that T1, T2 the 0 contained in the domain. So and you have to evaluate this thing. And by the way, this moment generating function exists, then the partial derivative also exists. And that's the theorem. That's the theorem, the partial derivative exists, and this moments are equal to that, and moments also exist since the partial derivative exists. That's why this moment generating function is so useful. This all the partial derivative exist in any order, and for the some special case, obviously that partial derivative of that m at the point 0, 0 with respect to say t1, the first coordinate is just the expectation of x, first coordinate. Similarly, the partial derivative, first partial derivative with respect to the second coordinate at the point 0, 0 is just equal to expectation of y. Similarly, the second coordinate, second order partial derivative with respect to the first coordinate, then it is just expectation of x squared, similarly like that. And this is second order partial derivative with respect to at the point 0, 0 with respect to the one for T1 and another for T2 at the point 0, 0 it is just expectation of x, x into. So everything that's covariance, variance, and every moments are actually uniquely determined by this moment generating function. That's why it's called moment generating function. Now, what is the utility of this? Okay, we know how to we know what is the moments and what is this, but what is the utility? The utility is so to show something, some for random variables independent using the distribution of PDF is tough, but using this moment generating, if this exists, then using moment generating function this is easy because the sum in various almost all random variable distribution is in our syllabus. This moment generating function is rather easier than the whole distribution. The moment generating function rather easy, some not complicated too much. The distribution may be complicated, but the moment generating function is slightly easier. So this theorem is it's very important theorem. If x and y are independent, if and only if this moment generating function at the point t1 and t2 is just the product of the t1, 0 and just 0, 2. This is very interesting, and that should be true for all t1, t2 real. So checking this is like actually easy, and it is just trivial to prove, because what is the moment generating function at the point t1, t2? It is just expected value of e to the power t1x plus t2x. So what is this? So proof this is very easy because it is just t1, t2. What is this? It is expected value of e to the power t1x plus t2y. But you know what is e to the power this? This is just e to the power t1x into e to the power t2x. Why? And since it is independent, and this e to the power thing is the Borel measurable function, it just take the two different products. So done. Just a y, sorry. It's a one-line proof. Conversely is a converse thing. Is left as an exercise. It's a homework exercise. Similarly, in that case, it is given that the m t1 t2 is equal to m t1 0 and 0 t2. Then we have to prove this is independent. So this actually needs the uniqueness thing. So these are very important theorems, and some examples are you can see in the book, in Rodke or any other book. You have some example. But before going to some example, we just state some theorems, which will be important for very important for the next for central limit theorem and this weak-law laws or other limits theorem. We just state this theorem because the proof of this theorem is not easy. The proof of this theorem is tough. So the theorems are like that. Some theorems we need for the next limit theorems. So theorem is like that: if let x1, x and y are two random variables, may not be independent random variables, and r is positive, some real number, positive real number, and if this expectation of mod of x to the power r and expectation of mod of y to the power r both exist, then this expectation of sort of Minkowski inequality needed. So it needs some Minkowski and Holder inequality. So it needs some strong or important inequality, which is called the Minkowski and this Holder's inequality, which actually prove this thing. Some mod of x plus y whole to the power can we write in this in the form of mod of x whole to the power mod of x to the power and mod of y to the power. That's some Holder thing, and we, you know what is Holder inequality for general cases. So that thing is needed for the proof. So it's some algebraic inequality. So we omit this proof. The next theorem, say theorem A, and the similar type of inequality is used. Here you have to use this Cauchy source also. That part is let now P and Q are two positive number. So P is positive greater than 1, and 1 by P plus 1 by Q equal to 1. This is called conjugate harmonic. This type of number is called conjugate harmonic, like 2. If P equal to 2, Q equal to 2. So it's called conjugate harmonic. Harmonic conjugate, sorry, it's called harmonic conjugate number. And this is very important for the complex analysis and this LP space, some functional analysis. Dual space, LP norm, different type of metric. We need some different type of metric, metric space in this convergence theorem. Basically, they are different sense of convergence is nothing but the convergence in different metric space, different metric, not only just Euclidean metric. And for the different metric space, with like I say LP or continuous function space, capital LP, capital Q. In that space, we need some dual thing like linear algebra. So it is like a non-linear space. So we need some conjugate harmonic thing. So LP dual is LQ, where P or Q are conjugate harmonic. That part we need actually. This analysis and this results we need. So complex conjugate part, the harmonic conjugate part. So this is PQ, such as is called conjugate, harmonic conjugate. Then if this is some P or Q are there, say 2, P equal to 2, Q equal to 2, then this is very important. This is actually called in its Cauchy-Schwarz inequality. That expected value of the mod, this is nothing but the less than or equal to expected value of, this is actually the generalized version of this Cauchy-Schwarz inequality, 1 by P. And this in Cauchy-Schwarz we use it's 2. Actually we use PQ2. If we use PQ2, that is a Cauchy-Schwarz, and basically is if we P equal to 2, Q equal to, it is Cauchy-Schwarz. And otherwise, for general PQ, it is actually Holder. So the Holder inequality is the generalized version of Cauchy-Schwarz inequality, as we know. So corollary, it's just if P equal to 2, Q equal to 2, then the Cauchy-Schwarz inequality. We have this CS inequality. So what is the Cauchy-Schwarz inequality? This expectation of x mod of xy is less than or equal to root over expectation of x square into root over expectation of y square. So this is important, mod of x. And obviously, if you just change x by x minus expectation of x and y by y expectation of y, what happens? But by the way, this the Minkowski also important for that. I mean, we need this Minkowski inequality also here. Holder, Minkowski, and Cauchy-Schwarz. Basically, Cauchy-Schwarz is just a corollary of this the special case of that Holder. So Holder and Minkowski are important, and we know what is Holder and Minkowski in our honors course. So if you just replace, now what happens? Just the color is this. We just replace. So what happens? We replace x by just expectation of x minus expectation of x, and just y by y minus expectation of y. Then what happens? Then this is expectation of this x minus expectation of x into expected y minus expectation of y. That mod value of that is just less than or equal to what happened? This is just a variance, root over variance of x into variance of y. And you know, this is just this is covariance part with the mod thing. So it is actually lies between minus of that to plus plus root over variance. So this is basically the correlation is less than lies between -1 to 1. This actually proves, because you just divided by that variance, root over variance part is the mod of this, the covariance part. So mod of the expected value is less than, again, this mod of expected value is less than the expected value of the mod. So mod of expectation x is less than expectation of mod of x. So if you use this, so mod of this covariance part is less than or equal to root over variance experience. So it is just mod of the correlation is just less than or equal to 1. That is the correlation lies between -1 to 1. That proves actually using this Cauchy surge inequality. So some general thing is there for using Holder and Minkowski, but I just omit these theorems because these theorems are only needed for our next things, limit theorems and this convergence theorem and different type of mode of convergence. In next lecture, we go to the different type of mode of convergence and this different limit theorems. Basically, the modes of convergence are the different type of metric. So the convergence in different type of metric. So we need that metric space idea, a different metric space idea for and the different norm linear space. So LP norm, LQ norm. If it is for discrete case, it's just a small LP norm, and for the continuous version, it is just capital LP norm. These are functional space. We need the different type of metric space on different type of metric other than the Euclidean metric on Rn. We need the other function space to get the idea of this different type of convergence, mode of convergence. We can write this mode of convergence in the real in Rn also, but if you look in the different metric space, then the convergence is actually looking easy in different metric space. So that will show in the next lecture.